Okay, given everything that we've learned so far, you should be able to pretty accurately sketch out a curve given a function. So our process is you need to find the domain, you need to calculate the x and the y intercepts, you need to check for symmetry, remembering that if f of negative x is equal to f of x, it's an even function and symmetrical about the x-axis. And if f of negative x is equal to negative f of x, it's an odd function and it's symmetrical about the origin with a 180-degree rotation. You need to determine the asymptotes. The vertical asymptotes are where f of x is undefined. Horizontal asymptotes, we're looking for what is happening as x approaches positive or negative infinity. Remember, we have seen cases where y can equal the asymptote, but what's going to happen is it's going to pass through the asymptote and then come back and approach it on the other side. So it's not just when y is undefined or f of x is undefined. For cusps, if discontinuities and vertical asymptotes have a first derivative that is undefined, make sure that you're stating those cusps. Then we determine the intervals of increase and decrease. Increase when f prime of x is greater than 0, and decrease when f prime of x is less than 0. We determine the local maximum and local minimum values using those critical numbers. When f prime of x changes from positive to negative, it's a max. When it changes from negative to positive, it's a min. And when it does not change sign, it is neither. We need to check for concavity and points of inflection using the second derivative, whether it's concave upwards, concave downward, or there is a point of inflection when the second derivative is equal to 0 at our significant numbers. And then we're going to sketch the curve, labeling all of the necessary key points. So here's an example pulled from your textbook where it graphs out everything that's going on with the graph, pointing out all the key points, whether it is a point of inflection, whether it is a maximum, whether it is a minimum, whether it is a cusp. So, given this example, it says, sketch a graph of a function given the following conditions. So what do we know? We know f of 0 is equal to 0, which means that the point 0, 0 is on the graph. We know that f prime of negative 2 is equal to f prime of 1, which is equal to f prime of 9, which is equal to 0. Because they're equal to 0, these are our critical numbers, and they are possible maximums or minimums. Not guaranteed, but because they're critical numbers, it could be happening there. We can see the limit as x approaches infinity for f of x is equal to 0. The limit as x approaches 6 for f of x is going to approach negative infinity. So we can see from this, we have a horizontal asymptote on the right-hand side, because it's approaching positive infinity, where y is equal to 0. We can see from this that because as x approaches negative 6, it's shooting off to negative infinity, there has to be a vertical asymptote at x is equal to 6. It says that f prime of x is less than 0 on negative infinity to 2, 1 to 6, and 9 to infinity, because this is our first derivative. This is showing us our intervals of decrease. When f prime of x is greater than 0 on negative 2 to 1 and 6 to 9, this is showing us our intervals of increase. When our f double prime of x is greater than 0 from negative infinity to 0 and from 12 to infinity, because this is our second derivative, this is telling us when it is concave up. And when it is less than 0, it's showing us when it is concave down. So let's take those f prime of x's. And what are the points it gives us? Negative 2, 1, 6, and 9. Negative 2, 1, and 9 were our critical numbers, and the 6 was our vertical asymptote. Our f prime of x went from negative to positive to negative to positive to negative, which means our f of x is decreasing, then increasing, then decreasing, then increasing, then decreasing. And when that change happened at the critical number, we know that that is a min, that is a max, that is a max, and the other one where it changed occurred at the vertical asymptote. We also know from the second derivative, where we can see it at 0, at 6, and at 12, our 6 is still our vertical asymptote. And in the other intervals, I have f double prime of x is positive, then negative, then negative, then positive. Which means that my f of x is concave up, to concave down, to concave down, to to concave up, which means that I have a point of inflection at 0, and I have a point of inflection that's going to occur at 12. So let's graph this out. We already have that point of 0, 0. We can see from here that that point of 0, 0 is going to be a point of inflection. We're going to have a vertical asymptote at x is equal to 6. We're going to have a minimum at -2. We're going to have a maximum at 1. We're going to have another maximum occurring at 9. And we're going to have one more point of inflection occurring at 12. It starts out concave up and is decreasing until -2. It is still concave up, but it is increasing until we get to 0. It switches to concave down up to that maximum at 1. And then it's going to stay concave down as it approaches that vertical asymptote. It's going to be concave down until the next point of inflection. And then it's going to switch to concave up. And it's going to approach 0 as it goes off to infinity. And that's what our graph should approximately look like, with a vertical asymptote at x equals 6 and a horizontal asymptote at y is equal to 0.